All right, students, we had questions about the Euclidean algorithm. So again, Euclidean algorithm is just a way of finding the GCD. So that is the goal of the Euclidean algorithm. And we'll kind of demonstrate it here on a couple of these pieces. You can use it anytime. You can use it literally anytime. Some people prefer um, to use it in specific instances. So I'll kind of demonstrate why I think there are times where it might be a good one to use and why sometimes it may not be a great one to use. So again, it's just a tool, and it's a tool that you can use. So what we're going to do is here, we're going to basically say, remember, here's the essence of what we're using, which is theorem 4-2, part C. And what does it say? It says that if D divides a number and D divides another number, then D divides A minus B. So again, that's the theorem that we're looking at here. Okay. Well, now, of course, what does that mean? Well, if your number, whatever your number is, let's just say that we have some big number, we'll say 3, and we know that it divides 2, 1, 3, 7, 2. Okay, so here's a large number, and 3 does divide this number. And we also know that 3 does divide some other number, and we'll just say that it's the number 6,000, just as an example, because we know 3 does divide 6,000 as well. Well, then that says that 3 must divide 21,372 minus 6,000. Okay, but that result is a new number. So when you see A minus B, that result is a new number, and it's typically smaller than A. So in this case, it becomes 15,372. So now we could start this process again and say, well, now I know 3 divides 15,372, and I know 3 divides 6,000. So I could repeat the process, and with these two pieces, I could repeat that and say that means 3 must divide 15,372 minus 6,000. Okay. Well, but what is that? See, this is just another number. When you subtract it, it's 9,372. So now I know 3 divides 9,372. Well, if I keep going with that, I could repeat again with 6,000 and 9,372. And when I put those together, now I know, based on the same theorem up on top, if it divides two numbers guaranteed, then it has to divide the difference. Then I could do 9,372 minus 6,000. And when you get done here, you end up with 3,372. And we know 3 does divide that number because of the theorem. Well, here comes the interesting part, and this is where the Euclidean algorithm kind of tries to simplify things a little bit. If we had started with 21,372, and we said, wait a minute here, it looks like we're making groups of 6,000 repeatedly, and we're just kind of removing those groups and ending up with what we could kind of consider as a remainder. Then we could say 21,372 is really 3 groups of 6,000 plus a remainder of 3,372. Now again, the Euclidean algorithm says, hey, if 3 divides this number and 3 divides 6,000, then it guaranteed has to divide the component here. If you want, you could bring this to the other side and say it's really 21,372 minus 3 groups of 6,000, because that's really what it is. And that gives you 3,372. This is kind of your remainder. So the Euclidean algorithm is a way of using division in the form of repeated subtraction. It's like take off 6,000. There it is. Take off another 6,000. Take off another 6,000. Take off as many as you want. And then you could repeat the process now, because now I have a new number, 3,372, and I have 2 other numbers that I know 3 does divide. Euclidean algorithm says take the smallest 2 and repeat the process. So 6,000 is a certain number of groups of 3,372 plus some remainder. And so that's what we're kind of doing with the Euclidean algorithm, is we're kind of shrinking our numbers down to find what goes into all three. So the general rule is that. Now let's see it applied a couple times. Let me clear my drawings off here. We'll go back and throw just a little bit of white space over here. And so I'm going to take a look at these two questions right up here. This is question 16. It says find the GCD, and it doesn't tell you which method to use. So you could really use any method at all. So for the problem 24 and 52, if I'm trying to find the GCD, I could spend some time doing some prime factorization, right? 6 times 4, which is 2 times 3 times 2 times 2. And I could come out here and I could do prime factorization. And 52, I can see that's 2. 2 times 26. 26 is 2 times 13. Okay, so then I end up with 2 squared times 13. I could find the GCD of 24 and 52 by just taking the smaller of the exponents. So in this case, it would be 2 squared. But what would that look like if I did the Euclidean algorithm? Well, if I do the Euclidean algorithm, I don't have to go through and do prime factorization. Depending on the numbers, that might be a really good thing. So here, if I was to do this, I would take my big number and say 52, and I'd ask how many groups of 24 can I make, and what's my remainder? So as you go through and do this, you could say, well, wait a minute. 52, well, that's 2 groups of 24. And right up above it, I'll kind of write that down just so you can kind of see that's worth 48. And the remaining piece, what's left over after that, is 4. Right? Because 48 plus 4 is 52. So now whatever your common divisor is, whatever your GCD is, it has to divide 52 and it has to divide 24 because that's what we're looking for the GCD here. And if it divides those two, by definition, it must divide 4. And this is where we get to use a little detective skill and say, aha, well, if it divides 4 and 24, then I could repeat the process. And that's all that we're doing with this. And so we just rewrite it. So how many groups of 4 are there in 24? And we would say, oh, there's 6 of those. 6 times 4 is 24. And there's a remainder of 0. And so now, whatever this divisor is, we could say our divisor has to divide 52, whatever it is, and it has to divide 24. And from those two, we know it has to divide 4, guaranteed. And then our last little piece says, oh, and by the way, your divisor also has to divide 0. But this is the one where as long as our divisor is bigger than 0, this one at the end is always true. Okay. So if this one's always true, then you work your way backwards. This is the first one that may not always be true, but what I need is I need my number to divide 4, and that is why our common divisor is 4. So really, it's the remaining piece you have left over, the first remainder before 0, and that's how you can find the GCD using the Euclidean algorithm. So let's see here. If I was doing that, again, I kind of just went through and every time I do these processes, I do quite a bit of explanation with it. If I was not doing explanation, it would probably go quite a bit quicker. And so when you get used to the Euclidean algorithm, you can really use it anytime. And so if I was doing this, I would say 52 is equal to a bunch of 24s plus a remainder. 2 24s, that's 48, leaves me 4 behind. Bring it down, 24. Oh, 24 is 6 times 4 plus 0. So there's my GCD. And I could find it, and it'd be that quick. Okay, we can also try it on numbers that are a little bit larger. So this is the chapter 4 review, but we could go back and try it on really on any 2 numbers. The next 2 numbers it says is 57, 67, and 88. Yeah, oh, 44, 53, 44, 53. Okay, so here we go. Let's grab a little white space. Okay. And there we go. All right. So if I was using the Euclidean algorithm here, remember, I'm trying to find some number that divides 5767, and that same number has to divide this. I got to tell you, I do not want to spend my time prime factoring. I don't want to. I want to try to make this easier on myself. So I'm going to use the Euclidean algorithm. 5767 minus or equals some number of 4453s plus a remainder. And let's see if we can figure those out. So 5767, I could do one time, one group of this. Then I'd have to subtract 4453. Oh, it actually matches up really nicely if you go to subtract because they there's no regrouping. So 1, 3, 1, 4. There we go. All right. So what am I going to do? All I'm going to do is say, okay, so I bring down the 4453 and I bring down the 1314 and I repeat. 4453, the numbers are now smaller. That's how many groups of 1314 plus a remainder? Well, let's find out. Let's see here, 44. So if I was doing this one, first off, this would definitely be on the calculator portion of the test. Let's jump into Desmos. And that's important. Let me bring that down just a little bit there. Okay, so Desmos is going to get me graphing calculator. Oops, I gotta make sure I click the right button. There we go. And so I want to do 4453 divided by 1314. Okay. And so let's see. Oop, I might have to move the rest of my work down. So here we go. Let's get that one out of the way, this one out of the way, and we'll just bring all the other stuff down a little bit out of the way here as well. Okay. So it says it goes in 3.38 times. Okay, well that's a reasonable number. So now as I come down, I'm going to say it goes in 3 times. And then I do have to do a little bit of work here to figure out the remaining piece. So I would say 4453 minus the 3 groups of 1314. And so I get 511. Okay, so 511. I'm going to write that down. That's my next component. Okay, so next, here I go. What do I bring down? Bring down the 1314, bring down the 511. So 1314 is equal to a certain number of 511s. And again, at any stage, I could stop if I happen to see a number that divides all of those perfectly. Yeah. I don't see one right away, so I'm going to keep going. Let's see here. 511 times something has to go into 1314. Okay, well, I don't know how many, so I'll just jump over to my calculator one more time. And I'll come over here and I'll just get rid of what I had. And here we go, 1314 divided by 511. Ooh, 2.57 it says. Okay. So what does that mean? That means if I'm jotting these down, it means it's 2 whole groups and then there'll be a remainder. Now, what I like about this is you can really kind of choose what kind of remainder you want. So I'm going to say 1311 1314 minus 2 times 511. My remainder is 292. Okay, so here we go, 292. And then I would bring this down and I'd have 511 equals a certain number of 292s plus some kind of remainder. And I dropped the red, I guess, on that one. So nothing really special other than I just forgot to change my pen color. Do my division and see how many times it goes in. So now right up here, I would say 511 divided by 292, and it's 1.75. Okay. All right, well, that's fantastic. So why don't we come here and we have one whole group of that, and then 292 leaves me a remainder of 219. Okay. And if I choose to, I still don't see anything that's in common between these. I really don't even see any really good common factors, but the nice thing is I'm getting much closer. The numbers are getting very small at this point. And so this would be one of these plus some kind of remainder. And so now I can jump up here and say 292. I want to do 292 minus 219. And I just got to get rid of the first numbers there. And we say, oh, 73. Well, that's fantastic. Now, I could absolutely keep going here. But one thing that I happen to notice is that 73 is prime. So when I get down to a number that's kind of prime like this, and we could certainly go, I'll show you. You would definitely go down one more. 219 is equal to how many groups of 73 plus a remainder? And then jump up and grab your calculator and say, well, how many times does it go in? And you would say 219 divided by 73 is 3 exactly, like right on the nose. So if it's 3 exactly, I would put 3 here, and my remainder would be 0, and boom, 73 has to divide all those numbers. Yeah. Okay. So that's it. That is the Euclidean algorithm. This is how you can do it. Again, if I was forced to not use the Euclidean algorithm on these problems, I would have to probably take the square root of 5767, come up with a number, and start checking prime numbers all the way up just to find some kind of prime factor. And that seems to me like an absolute lot of work. Square root of 5767 is up to 75. Oh my goodness. Oh my goodness. Like if I had to do this, I'd have to go up to 75.94, which means if you go back to that colorful sheet that we had of all the primes, you'd have to do 2, 3, 5, 7, 11, 13, 17, 19. You got to check all of these. 23, only a few of them have tests, not very many. 29, 31, 33, 35, 37, 39, 41, 43. You have to check all of them. You have to do the division every single time. 43, 47 is good. 49, not 51, no. 53, no. 55, 57, no. 59, yes. 61, 63, no. 67. 69, no, 71, 73. Okay, there we go. You would just get to check all of these numbers. So you'd be off over here saying 5767 divided by 7. 5767 divided by 17. 5767 divided by, that's what you'd be doing. And when you're done, you still only have the prime factorization of one number. You then have to repeat that process for 4453. So again, why do we use the Euclidean algorithm? Because prime factoring is sometimes a real pain. It's just challenging. And so we tried different techniques. So let's jump back to 4.3. Okay, so here, I think there's some other numbers in this one in 4.3. So 14,560 and 8,250. Let me show one additional way that you can use the Euclidean algorithm. There's nothing wrong with these, with the with the ways that we just showed, but there is a way that you can utilize division and perhaps make it a little bit easier on yourself. So we're going to jump into Desmos a little bit here, but we're going to want to do, yeah, I think that'll be fine. So we're going to do 14,560 and 4250. Okay. So those are the two numbers that I want to check. I want to find the GCD of these two numbers. All right, so if I'm off on the side, I'm over here and I'm saying, okay, I got 14,560, and I think it's some number of 8,250s plus a remainder. And the question is, how many of these do I want? So when I jump into Desmos or whatever calculator you have, right? Grab a calculator and you can just do 14,560 divided by 8,250. And what I want you to see is this. When you look at the component that's left, you have 1.76. Typically, I would bring that over and I'd say I'd put one group in here, and then I'd have a remainder that is left. And so if we want to check the remainder here, we could say minus 1 times 8250. Okay, and that lets you know that your remainder is 6,110. So that's that's pretty large, but that would be my remainder, 6,310. Then I would repeat with these two numbers. And there's nothing wrong with that. There really isn't. Um, other than if you realize that your number was 1.76, you could have gone and used a different multiple. You could go over a little bit. And the reason is it doesn't have to be addition here. It could also be subtraction. So you could overshoot to get a smaller number second. Let's show what that looks like. Let's do two groups of 8250. Okay. So here we go. All I'm going to do is go up here and I'm going to say instead of one group of 8250, I'm going to do two groups of 8250. And what do I notice here? I notice that my number is now 1940, but it is negative. So I would say, okay, then I take away 1940. So this number would be too big. So instead of having to deal with the number 6310 and taking one additional step to get to 1940, I jump to 1940 right away because I just rounded up. Now, when I bring the numbers down is 8250. Oops, that's a 5. Sorry about that. Went a little too quick. And I say, how many groups of 1940? It's the same question, really, but I can jump up to my calculator and just type that in and say, well, let's check it. 8250 divided by 1940. Okay, now the number is 4.25. So this number is much closer to 4. So instead of rounding up to like the other one was 1.76, so I would round that up to 2 so that my remainder is a little bit smaller. And so what you could do here is just say, well, I'm going to round this one down to 4. And so I have 4 groups of 1940. And let's see if I come up here on top and delete, I'd say minus 4 groups of 1940. And that leaves me a remainder of 490. So that's a pretty good one. And that'd be plus 490. And again, I could bring these down and I do 1940 equals so many groups of 490 and off we go. We'll do that check really quick. So I'll say 1940 divided by 490. Holy cow, look at this number. Oh, this is where the power of what I'm showing you comes in. This is 3.95. It's so close to 4. If I use 3, my remainder is going to be pretty big. But if I use 4 here, then my remainder will be negative, but it'll be very, very small. So I'm going to do 4. And I want to show you how much different that is. Okay. So watch this. If I say minus 3 times, my remainder is 470. If I say minus 4 times, my remainder is now 20. And 20 is so much easier to work with than 470. So now I can bring it down and say, okay, so I'm getting down here in a couple steps, whereas the longer method would probably take an extra 1 or 2 steps along the way, maybe 3 steps, depending on how many there are. So I'm now at 490. That equals a certain number of 20s plus a remainder. And actually, you know what? Okay, I could keep going. You can absolutely keep going, right? So I'm gonna put a little star here because I saw something here that made me say, that's helpful, right? And I want to kind of share that with you because you can do the Euclidean algorithm all the way down every time, or you can sometimes stop because you spotted something. So here, if I was doing this, I would say there's probably 24 of these because that would be 480 plus 10. Then I bring the 20 down, and the 20 is 2 groups of 10 plus a remainder of 0, which means I have to end up here. So again, that's probably the kind of going to the end of the algorithm every time. Go until you hit 0 as a remainder, come back 1 step, and that'll be your GCD. But the reason why I flagged this step here is whatever my number is, whatever that GCD is, it has to divide 20 and it has to divide 490. So instead of these huge numbers at the top, I now have 490 and 20. And I got to tell you, that's 49 times 10, and that's 2 times 10. And if you notice what I noticed, which is 49 and 2 have nothing in common. What they do have in common over here is a common 10. So I could stop there and say the GCD is 10. Now, you could certainly keep going for 2 more steps to find that, but the second you see something in common like that, you can check it right there. You might have been able to pick it up on the step before that, depending on how good you are with your multiplications. 1940 is equal to 194 times 10, and here 490 is equal to 49 times 10. And the reason I say this is 49 is 7 squared. So the 10s are already in common. So I know my GCD has to have a factor of 10, but this is 7 squared. And all I have to do is see if 7 divides in here. If 7 goes into 194, then I have another chunk that is part of the common divisor. So all I would do is I would say 194 divided by 7, and I get a decimal number, which means it fails. And then you're actually done right here. Because the two numbers that you see on your screen, the 194 and the 49, they have nothing in common. So your GCD could just be the 10. So feel free to stop at any point in time when you see something in common. And let me see if I can do one more of this. I think one that I did a moment ago was 24 and 52 was one of the ones that I did. So if I had to do 52 and 24, right? And I'm using the Euclidean algorithm, and I say, okay, this goes in 2 times. Again, that's 48, and I end up with 4 remaining. I don't really have to go to the next step if you notice that 4 divides into 24 perfectly, right? 4 is a divisor of 24. 24 is a multiple of 4. And so right there, you could stop and say, got it. My GCD is 4. There you go. You can use the Euclidean algorithm all the way down to the end. You can use it in steps to make your numbers smaller and easier to work with. And again, something like this might be a very efficient way of helping you find GCDs. But again, you can always find factors, right? Even if you don't see prime factorization all the way to the end, you can still sometimes find the GCD pretty quickly. Right? So if we had the number 78 and I had the number, what do I want to do here? I don't know, 27, something like that. I could say, okay, what do they have in common? Maybe I don't see anything right away. I can choose to start prime factoring, or I could choose to go a different direction. So right off the bat here, if you choose to prime a factor, there's nothing wrong with it, right? There's nothing wrong with it. But if you said, let me try the Euclidean algorithm and see how many 27s go in, even if you don't see the answer to this right away, take your calculator and do 27, or let's see here, 20, what am I going to get? 78 divided by 27, and I get 2.888889. That's almost 3. So if you would have said that this is 3, let me change that to blue. If you would have said this is 3 times 27 is 81, then this piece over here would have to be a -3. And then you could say, wait a minute, 3 goes into 27 perfectly. So my GCD is actually 3, and you'd be done. Okay. Now, if not, you would say it goes in 2 times because you're just going to round down. And 2 times 27, that's 54. And then 78 minus 54 is 24. Then I bring the 27 down, the 24 down. How many 24s go in here plus a number? And you say one of these, and it's a remainder of 3. Then you bring the 24 down. If I'm going all the way, this is what it would look like. And that's 8 times 3 plus a remainder of 0. And the remainder right beforehand is 3, and it would match the GCD. So again, if you spot something, use it. Okay, it's not meant to be something that's necessarily overly challenging. Okay, and again, it's just another technique, right? Just another technique. So any of these that you see when it says use prime factorization, use set intersection. First off, set intersection is really, really time consuming. It might be great for small numbers, but it's absolutely horrible for numbers that that don't have much in common. Like this, I remember writing the answer key to this and saying to myself, I think I need to change the problems because 18 and 58 for the intersection of sets method means you have to write 18, then 36, then 54, and I have to keep going until they intersect in a number. But if I was to stop and say, wait a minute, 58 is equal to a whole bunch of 18s, maybe I can get through this a little bit quicker, right? You say, well, how many 18s would it be? Well, jump over to Desmos and say, let's take 58 and divide by 18. It says 3.222. Got it. So that is 3 of them. And 3 times 18 is 54. Guess what? There's a 4 left over. Now, could I continue with the Euclidean algorithm? Sure. But whatever my number is, whatever my divisor is, it has to divide 4. And that same divisor has to divide 18. And that same divisor has to divide 58. Well, there's not a whole lot that divides 4, right? It's a 1, a 2, and a 4. And here's a hint. Everything is divisible by like 1 goes into everything. So that's kind of like we just wait on that one. We can see all these numbers are even. So I do know 2 goes in. So those are good to go. The last one is 4. I can see 4 goes into this number, but 4 does not go into 18. So therefore 4 is out and my GCD is 2. You can also get that same result if you chose the prime factoring approach. So there's a lot of different ways you can find this number. 18 is 2 times 9, and 9 is 3 squared. 58 is 2 times 29, and then it ends right there. Now all you're doing is looking for common pieces. They each have a 2. That is the GCD. Use that smallest exponent. All right. So I think a bigger question, if you're doing Euclidean algorithm, is probably like, when should I use it? And the answer is you can always use it. You could use it as your first step to make things easier for yourself as you go down the road. If the numbers are too big, use the Euclidean algorithm. So if I was doing something like this with 3 numbers, maybe I don't want to prime factor every one of them. Even though this example in the book says, please use prime factoring, maybe I want to say, hey, you know what? I think I want to do something a little different, right? So I would take maybe 800 with 75, and I'd say, well, how many 75s can I get into 800? Right, so I grab my calculator and I say, okay, let's check that. Let's see here. So 800, and I divide by 75, and it says 10.667. So then I would say, okay, let me multiply it by 11. So what I have is 800 minus 11 times 75, which gives me a negative 25. Okay. And then, to be honest, I would probably stop right there because I need something that divides evenly into 25 and 75. And that one I can do in my head. It was harder for me to do 875. I don't know that one right off the bat, but 25 and 75, oh, hallelujah. The GCD is 25. So I just found the GCD for the first 2 numbers, and now all I have to do is 25 with the number 450. But again, the test for 25 is just the last 2 digits. 25 goes into the last 2 digits, so 25 becomes your GCD. So again, use it. If you're doing 103 and 320, that might be challenging, right? Maybe you don't see that 103 is prime. So you could just say, okay, let me just do one of these. How many groups of 103 can I bring up, and what's my remainder? And if you do this math, you'll see you can do 3 of them, because 3 of them becomes 309, leaves you with a remainder of 11. So don't keep going if you don't need to. You need a number that divides 103 and a number that divides 11. This is your ding 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 win 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 win, because you know 11's prime and you also know a test for 11. So if you want to test 11 with 103, you would add the components going up, you'd get 4, add the components going down, you get 0. 4 minus 0 is 4. And I got to tell you, your divisibility test for 11 shows that 11 does not divide 103. And because the factors of 11 are 1 times 11, You tested 11 and it didn't work. Here you go, folks. Your GCD is 1. Okay. So again, that's what I would recommend. Are there other approaches? Of course, there's other approaches. If you haven't seen that in this class, there's always going to be other approaches. But if you had to do, what other numbers did I do? Did I just do that one? Yeah, I think I did. So if I had to do 140 and 320, maybe I would say, well, I know 140 and I know 320. And I know that's 32 times 10. So notice I'm not jumping to the prime factorization right off the bat. It's okay to find factors that just match up perfectly. Now 14 is much easier because it's much smaller. That's a 7 times 2. And down here, this is a 2 times 16. And then all you have to do is compare. Hey, I have 10s that are common. I have 2s that are common, and then I happen to have a 16 and a 7, and those don't have anything in common. So my GCD is 2 times 10, which is 20. And that's how you can get there pretty quickly. All right. So a lot of techniques to use. Hopefully you find a couple of them very effective and you would practice them a little bit. If you have other questions on this, please let me know. Hopefully this gave you a good idea about the Euclidean algorithm and also the idea that you could go up or down. And just as a reminder, if you do check back in the textbook tends to treat this as not allowing negative numbers. And that's why for all of their Euclidean algorithm pieces, I'm going to go back. I think it's one more page. Here it is. For all of theirs, they treat it as standard division. They would never go and round up. If you were doing this problem with 10,764 and the number 2,300, though, you could have rounded up. And I believe if you round up on this one, you will jump straight down to you'll go from this first problem right down here to find 736. You will never find 1564 because you don't need it. And then that'll actually shrink what you do next. So you can save typically 1 to 2 steps in a problem like this. If it's one that's a little much longer than that, you might save 3 or 4 steps. So again, work smarter, not harder. All right. Hope that helps. Let me know if you have questions. Off you go.